On.
Hello, thank you for inviting me here. My name is Ilya Shpitser. I'm here at the Future of Humanity Institute, and I will talk about decision theory and causal graphs. So I'm not a decision theorist or a philosopher. My background is computer science and statistics. I'm a statistics lecturer now. So causal inference is the angle from which I will approach this talk. And so, I apologize in advance, of course, if I say stupid things because I'm not in the field. So, what is decision theory about? It's we want agents that act optimally, quote unquote, and that could be construed in various ways. This is lots of fields worry about this problem. People in AI obviously want to build intelligent agents that act well. People in philosophy worry about this a lot. People in social and cognitive sciences worry about it in the context of human behavior as well. Economists worry about this as well, of course. They usually make various optimality assumptions on agents. To act well, we need to know things properly. So we need a good epistemology, whatever that means. Historically, there's been a bit of an analytic approach to this problem, and by that I mean analytic philosophy, and by that I mean people argue about examples. And so this is not, I'm not really up in my philosophy literature very much. The one instance of this approach that I know about as a causal inference person is the actual cause problem, which is what does it mean for one event to actually cause another, and that would be something like, they have these desert traveler examples where, somebody's traveling in the desert and they have a canteen with water, and then somebody poisoned the water, and then somebody shot the canteen and the water fell out, and the person is alive, and the question is what actually caused them to be alive. And so these are the kinds of, so people can make endless variations of these things. And so people use this kind of approach for this problem as well, for decision theory. They come up with variations on things that make a particular decision theory fail in the hopes of eventually having this process converge in something sensible. And there's also concern with exotic scenarios, with anthropics, as I call it. So things like the Sleeping Beauty problem and things, what I call counterfactual copies. And what I mean by that is just the kinds of things that Newcomb's problem is meant to highlight, basically. And there's no consensus, because why would there be consensus in philosophy on anything? That's the intro, but I'm sure you guys know all this. So what will I do in this talk? I will concentrate on non-exotic things, mostly, except at the very end. I will concentrate on evidential and causal theories. And I will talk about EDT, because I don't like EDT very much, as you can probably tell from my background. But importantly, I realized that the version of EDT that I'm presenting is a straw man. And part of the reason I'm here to give this talk is I want somebody who likes and understands EDT well to sit me down and explain to me what a steel man of EDT is like. Okay, and my worry is that, as you will see, the things that causal decision theory gets right goes far beyond things like smoking lesion, which is a standard example that people think that it gets right. In fact, there is a very sophisticated, quote-unquote, factory of examples that I have, that I can generate with very non-obvious answers that causal decision theory will just do, or at least a version of causal decision theory that I'm going to talk about gets correct. And so, if you want to, it's possible for smart people who like EDT to repair it, to apply to smoking lesion, but the point is that's not enough. You also need it to repair it in such a way that it applies to all these other examples, infinite examples in my factory. And the worry is that if you do that, you will eventually just have something isomorphic to CDT with a different terminology. And so this is what I really want to understand. Is that what is actually happening, or is there some alternative that's genuinely different? Okay? So that's part of what I want to understand. So this is educational for me as well. So I will give an interventionist formulation of CDT, where I call I-CDT. I will talk about what that is, because interventions is how people from my neck of the woods think about causality. It's not the only way, there are other ways, but I will try to give some justification for why this is sensible. I will discuss progress on I-CDT as a template for progress in decision theory. And of course, this progress has not been made in the context of decision theory, it's just been made in the context of figuring out what causal effects are. And that's a problem of great interest in medicine and epidemiology, because in medicine, you give somebody a drug, you want to know if it works or not. So that's a causal problem. And in medicine, also, you cannot experiment on people. So usually in statistics, the way you figure out causes and effects is you randomize. You do random treatment assignment. So Fisher, who is the grandfather of statistics, he worked in agriculture. In agriculture, because that was sort of the area of application in statistics, and there, you would think of problems like you have two separate fields that are basically the same, and you want to apply a fertilizer to one and maybe apply something else to another, and you want to see what the yield is, and that's your outcome. And it's easy to randomize there because they're fields and they don't have feelings. If you give it a bad fertilizer, that's okay, but you can't randomize people into a smoking group and a non-smoking group because we have laws about that. And maybe randomization is just expensive. If you want to randomize one country to this tax rate and another country to this other tax rate, then that's just a non-starter. So you need to use observational data. And so people have been thinking about this problem very hard for a long time. And this is not really particularly a decision theory context, but the point is I could easily make it to be about decision theory by just putting utilities in. And all the same complications remain. And so I will discuss Newcomb's problem because Newcomb's problem is a famous example where ICDT fails. And I'll have something maybe slightly novel to say there. And I'll have to talk about conclusions. So let's start with EDT, which is what I will be beating on today. This is a straw man of EDT. I realize that there are more sophisticated versions of EDT. But the typical phrasing is we act to maximize expected utility conditional on your act having taken place, quote unquote. And so my straw man of EDT will interpret the statement to mean that we have some sort of data, historical data on how people have acted in the past. And from this data, we can construct a joint distribution. And from this joint distribution, we get a conditional distribution of the outcome given the actions. And we will maximize utility with respect to this conditional distribution. This is a straw man, I understand that. But that's what I will use as a simple thing to explain. And this will obviously fail, as you will see in a second. There are variations on this, and one variation that people often say, especially people of a Bayesian persuasion, is that you should condition on everything that you know is the case, because you should use all available evidence. This is something Mr. Don Rubin says. Donald Rubin is a very famous Harvard statistician. He developed something called the Rubin causal model that I will talk about in a second. And Rubin is a Bayesian, and Rubin says, of course, we should condition on everything, and so there are variations of this where you don't just condition on actions, but on everything, on actions and on everything that you know. And Pearl, who is a good friend of mine, shall we say, disagrees with Rubin on this point, and I'll talk more about this disagreement later because I think it's an interesting disagreement. I'm still not entirely clear what's going on there. Okay, so this is our good friend the smoking lesion problem, where this version of EDT will fail, as we all know. I will use causal graphs to display this problem because I like graphs, because I have a very weak symbolic brain, but a very strong visual brain. And so I like to draw pictures to understand things. And part of the point of this talk is I'm trying to convince you that graphs are useful to use for complicated problems for this reason. Because I think many people share this feature of mine that their visual system is better than their symbolic system. It's just some accidents of our evolution. Sorry. So in this representation, our vertices are variables of interest, and our arrows, blue arrows, mean, loosely speaking, directly causes. I will make this a little bit more precise a few slides later. But intuitively, we all sort of know what directly causes means. So let's leave it at that for now. So in this problem, which I'm sure you all know, S is smoking, C is cancer, and L is some sort of gene. Smoking has positive utility, cancer has negative utility, but it's much worse than the positive utility from smoking. And this is a hypothetical problem, so in reality we know that smoking does cause cancer, but here there's a dashed arrow from smoking to cancer, meaning that the effect is weak or almost non-existent, and it's all about that gene. Okay, and these are the properties of the causal relationships in question. I wrote them probabilistically, that given that the gene is there, the probability of smoking is high, and given that the gene is there, the probability of cancer is high. And therefore, given conditional in the fact that you're a smoker, the probability of cancer is high. But it is the case that conditional and the gene smoking and cancer are independent. That's an independent symbol. I think it was invented by a fellow at Cambridge named Phil David. So it's kind of this orthogonality symbol. And the question is, should we smoke? So this is a standard problem. So the point with smoking lesion is L has already occurred and will affect C regardless of what we choose to do now. That's sort of the point that naive EDT, strawman EDT that I presented is not understanding. And so this is just an isomorphic, slightly isomorphic example. This is sort of the cargo cult example where you have crops. Crops are good because you can sell them, and you have rain, which makes your crops better. And you can also wet the soil at some expense because you have a sprinkler or something. And it is the case that the soil will be wet if it rains. And it is the case that you will get good crops if it rains. And therefore, the conditional probability that you'll get good crops given that you just sprinkled around some water is high. And so the question is, should we do the expense of sprinkling things around? But of course, we shouldn't, because that's kind of cargo cult thinking. Rain will happen or it will not happen based on whatever causal features make rain happen. And the fact that you're trying to cargo cult around with a hose is not going to affect that. And so you're just wasting utility on something that will not be affected by it. So it's basically isomorphic. So what's the problem? The problem is confounding. So lesion and rainy weather are confounders or hidden common causes. This is obviously well known. In statistics, it's a very old, very recognized problem. In statistics, they have to worry about this out in the trenches with, real data, as Benji says. And in statistics, they've known that if we randomly assign patients or fields to smoking or sprinkler arm or control arm, then confounding goes away. And this randomization is a very old idea. The original reference of something that looks like a trial is in the Old Testament, in the book of Daniel. And I think it was about nutrition, where the captives in Babylon didn't want to eat what they were provided. And they said, look, we'll just select a few people and we'll have our diet and you'll do your diet and then we'll compare. It wasn't a randomly selected assignment quite, but this idea of comparison is very, very old, thousands of years old. First formal randomized control trial known to me, and I'm not up in my literature, is due to a gentleman named James Lind, who was a Royal Navy physician, and he's famously discovered the nutritional basis of scurvy by taking a few sailors and making them as similar as possible. This was important. He actually pointed this out explicitly in his journal because he was worried about confounders. He wanted to have compatible sailors, so same age, same health condition, and gave them various things, and it turned out lemons worked for some reason. And this was a celebrated success in epidemiology and made Royal Navy much better than the navies of other nations. Classical statistical inference was developed for randomized control trials. I think Ronald Fisher, the father of statistics, basically brought it in statistical practice. And in RCTs, correlation is causation. Ordinary probability theory is enough. And so now we can talk about causal decision theory. So the typical phrasing is act to maximize expected utility with respect to quote-unquote counterfactual worlds where the action took place. I'm not sure if that's the best phrasing. And so we have this weird probability here, and it's not clear exactly how to formalize this probability. And I think there are actually multiple ways of doing it. And this is left unspecified. And Pearl, my good friend, says that you need more than probability theory here. You need some additional language. And this is actually a point of disagreement between Pearl and some people who like EDT, who thinks that if we're just Bayesian just enough, we can get away with just conditional probabilities somehow. And Pearl says that that's a hopeless project. And so that's one of the things I'd like to talk about with people who are into the Bayesian view, as to how right Pearl might be. So we're going to formalize this strange double bar conditioning in a particular way using something called potential outcomes and causal graphs. This is what a modern causal inference view of this is. Potential outcomes are first written down by a fellow named Neyman, Jerzy Neyman, in the 1920s. And they were a general causal model based on this was given by a Mr. Don Rubin at Harvard in the 70s. It's a very influential model. And potential outcomes are about interventions. What happens if I assign by outside fiat a particular fertilizer to a particular field, which is very different from if I happen to observe that the fertilizer is there. And causal graphs were first used by a fellow named Sewell Wright, who is an amazing biologist and geneticist. And he did it in the context of pedigree analysis for animals. And it was developed into a general model by a fellow named Shpitser and others at CMU, and by a fellow named Pearl at UCLA in the 90s. And there is a modern synthesis of two of these ideas. I think they're both important, by Pearl, Robbins, Richardson, and others. So, how are we going to formalize things? We will have this notation of y with the parentheses, and that means the outcome, let's say the yield of a field, given that we gave that fertilizer, which is little a, kind of by force. And people in statistics, they want a single number to think about, and so they look at like differences in means based on this. But that's just their cultural preference. You can do other things. You can just look at the distribution of this if you want. And we can obtain this directly if we randomize treatment assignment. But we can't always randomize because of minor ethics. And the problem is, how do we do causal inference for observational data? And my claim is that full solution solves, quote unquote, the CDT problem, if you're willing to buy my assertion that you want to use potential outcomes to represent this weird double bar probability. So I will go through this quickly. It's not so interesting. This is sort of the context. To the right, you have animals, which are vertices, and animals sire children. And so one is a parent of three. And actually, we use genealogic metaphor in graph theory in general, even if they're not parents and children directly. So one is an ancestor of 7, and 7 is a descendant of 1. So hopefully this is all clear. And Wright's contribution, remember, this is 1920s, where there were handwritten papers still. So he figured out that he wanted to know how inbred 2 cows were or something like that. And he figured out that if you assign linear regression models to all these things, you can assign regression coefficients to edges, and then this notion of inbreeding corresponds to a number, and this number corresponds to certain paths in the graph, to a sum of products of coefficients in certain paths. And in fact, what he discovered is the marginal version of something called d-separation that took almost a century later to fully develop. So he was quite ahead of his time. A modern synthesis of these ideas is we will use potential outcomes to encode cause-effect relations. In other words, we will encode things like what is a confounder, because we want to encode that properly to solve things like smoking lesion. We'll display cause-effect relationships using a graph, because at least my brain is not symbolically very strong. And I will give a complete answer to the following question. Given some data, and given some causal model underlying this data, what is the optimal treatment? And a lot of decision problems are of that form, I claim. For example, the smoking lesion problem is of that form. What is the right treatment? Should we smoke or should we not smoke? My point will be that this handles not just smoking lesion, but a very complicated factory of examples that I will describe some of these examples. They came up in statistics. And the point is, if you want to do something else, you have to also get all that stuff right, because that's all known. And so my claim is that if you want to be sensible and you deal with exotic problems like Newcomb, what you should do is you should generalize this. Or you should redo all that work yourself and make sure you get it right on all these problems. So none of this is exotic. This is all about confounding and things like this. That's going to be my claim. So I'm sort of willing to defend this claim. Okay, so graph terms. 1 is a parent of 3, 3 is a child of 1. 1 is an ancestor of 6, 6 is a descendant of 1. Just basic math stuff. These are siblings. That red arrow means that there is some sort of common cause, but I don't want to write it down because I don't want to clutter the graph. So instead, I'll just put that kind of arrow instead. And that just implies that 1 and 2 are siblings because they have a parent of some sort in common. And there's this important notion of districts, and that's connected sets via red arrows. So here, it forms a partition. This is the partition that it forms in this graph. I'll get back to this later.
Would 5 and 6 be siblings?
No, 5 and 6. 5 is a parent of 6. 6 is a child of 5.
But are they siblings via 2?
No. Siblings just means they share a red arc in common. So I will only choose to put red arcs between some things, but not other things. Red arc just means there are some hidden variables there, and I don't want to put them in.
Okay.
It happens to be the case in this graph that there are no hidden common parents with 5 and 6, so there is no red arrow between them.
Okay.
It's just a shorthand way of doing a DAG with hidden variables. That's all it really is. I didn't have to do red arrows. I could just put more nodes in instead, but I chose not to just in the interest of simplicity. Okay? And it turned out that it's convenient to think in terms of these red arcs sometimes. But it's all just definitions. It's not so important until later. Okay, so this is now comes to the point where I have to justify myself a little bit. So the first thing I'm going to say is that people sometimes conflate statistical and causal models of a graph. I think Ilya Shpitser did it once in a post of his, which he has yet to correct. A statistical model, as us statisticians understand it, is just a set of distributions. That's just all it is. A statistical model of a graph is just a set of distributions that Markov factorize. You may have seen this around. That's, people call it a Bayesian network sometimes. Our good mutual friend Yuda Pearl came up with these in the 80s in general. So this is not a controversial thing because that's just some convenient statistical object that statisticians like. This is convenient mathematically for ways that are not important for this talk. So I'm not going to talk about this part very much. What I will talk about is this thing at the bottom, which is a causal model. So the first thing I will say about it is that it's different object from a statistical model. And in particular, it makes more assumptions. It assumes this, which is fine, but it assumes many other things as well. In particular, it makes an assumption about what the potential outcome is if I intervene on some A, on a bunch of things, on a subset of V that are A. And the assumption that it makes is what this is equal to is you look at this original factorization and you drop all the terms corresponding to A. Okay? So this is just a definition, and you may or may not choose to accept it. And I will accept it for the purposes of this talk, and I will try to justify why a little bit. Although this is actually a whole separate talk about why we should accept this definition. So this is actually very important, and everything will be driven by this. I'll call this 2, equation 2. This equation 2 says that there is a link between observed data, which is stuff on the right. These are all conditional distributions. I can get it from frequencies that I see, or I can get a posterior for this if I'm a Bayesian. With things on the left, which are causal things and which are results of hypothetical interventions. So these are very different things. And this assumption asserts that they're the same in this particular way. So this is what the causal model is, that assumption. And so we have to justify this assumption, and I will give some justification here. Oh, and these are some examples of how these things factorize. So this is the factorization of the overall graph statistically, and here's what happens if I intervene on C. I just drop the term for C given A. And that's what 2 will assert for that, but it actually asserts it for all subsets. Okay, this is called the truncated factorization, or the G formula, or the manipulated distribution by different authors. Why adopt it? So what we want to express is that J points to I means that J is a direct cause of I. And so the intuition is that this factor that we drop, if we intervene in A, is the mechanism for I, the causal mechanism for I in some sense. And if we want to intervene in I, if we want to smoke, we're deciding to ignore the usual things, the usual predilections of mine that cause me to smoke or not. Well, I disregard my habits, and I'm just going to pay attention to the assignment. So I'm going to make that thing a constant. And making it a constant involves dropping that probability and just replacing it with a constant instead. So that's the intuition for why we drop those terms. So that's one way to do it. The other way is that answers agree with intuition. And I'm not going to get into that into too much detail. We can look at the epidemiology literature, where I think it's been found to be the case. The other encouraging thing about this definition is that it came up in lots of places. It came up in epidemiology. They call it stratification there. In information theory in channels with feedback, that's fairly recent in the 90s. In statistics, in survival analysis and missing data, it's the same idea. And in AI, in something called Thompson sampling. There is a nice Wikipedia article on it. And this is a special case of Lewis's imaging, and there is a discussion in Perl on this. And so if this probability is what happens if we decide on A, so this is going back to decision theory, then what is this? And this sort of means, this is what evidential decision theory looks at, the history of cases in the past. So the solution of smoking lesion, if we use that definition, is just to maximize this, given that that probability is given by the potential outcome. And so this is equal to this. And 2 directly implies that formula over there. And that formula is different from the conditional distribution given that smoking was observed. That's why they give different answers in this problem. It turns out in this case, by assumption that smoking is independent of cancer given the lesion, and that means that the probability of cancer is unaffected by our choice. And so smoking has utility and does not affect cancer, we smoke, which is the sensible answer in this case. Okay, but you guys all know that. I'm just kind of writing a little bit of formulas to kind of underpin this. But here's the point. Because I did this as a graph, I can make this graph bigger if I want. I can make this graph arbitrarily big. And I don't have to, I'm no longer tied to a compelling story. I could just pose it as a mathematical thing and say, what's the right thing to do with this graph and this data? And that allows me to create very complicated problems with very complicated answers. And here's one example from history that people have gotten wrong for a long time. This is called the healthy worker survivor effect problem. This solution is by Robbins, Janie Robbins, my former boss, in '86. And the graph looks like this. So there's a utility at the bottom, but it's not so important. You get some utility from the outcome and some utility from your actions. Okay, so A and B are asbestos exposure over time. And I say that it's plus utility because asbestos is an insulator, so it's advantageous to use it if it wasn't bad for you. Yeah. And S is intermediate health measure. And Y is the outcome. And the outcome is negative because asbestos makes you sick. Okay, and L is an unobserved health level. Okay, so that's the graph. So it's a slightly more complicated smoking lesion with basically a single extra node. Okay, I guess 2 extra nodes. So, and we think that A and B affect Y, and moreover, we think that A and B affect Y negatively because we have a suspicion that asbestos is not great. But the thing is, people who get sick earlier from asbestos stop working because they're sick. That means that people who are left until the very end happen to be healthier because of their differences in L. And so it might seem like asbestos is actually good for you if you look at the observed data. So this is another instance of this confounding problem, but it's more complicated than before because the graph is more complicated. So the question is, what's the right answer for this decision theory problem? So we must use 2 properly, given this graph. So it all relies on us agreeing to use 2, the equation 2. So one thing you might want to do is you might want to do naive decision theory, naive evidential theory, and just condition on A and B, which is wrong because of the confounding thing. So it's wrong for the same reason that that answer is wrong in the smoking lesion case. Okay? We could also we may have heard naively that if you have a confounder S, which it is for the purposes of B, you should adjust for this confounder using that formula. But it also turns out to be wrong in this case because the graph is different. So in this graph, it was correct to adjust for L. So I have that formula. But it's not the same as this graph, so you don't do that. The other naive thing that I've heard from somebody at MIRI is that it's not naive, it's just, I think, not smart enough, let's put it like that. We could try to measure L. The problem is this L is not observed. So if we could observe L, we could just, and we agreed to use 2, we can just observe it and then use 2. And that's a non-starter because it's silly to require that we observe everything that needs to be observed to make decisions because that's just not how real world works. Everything is going to be unobserved. So you have to deal with it. So the right answer actually happens to be this, where it's almost like an adjustment, but you have this extra conditioning of S given A. And I'm not going to prove this to you here, but I would just say that this is a consequence of 2, a logical consequence of 2, given this graph and given the fact that L is hidden. And so Robbins figured this out a long time ago, and until he figured this out in '86, people were using this and were getting biased answers, basically. And this is not a philosophy thing, this is like a statistics thing. They were just wrong about this. Okay? So this is an example of a causal decision theory problem that until people thought hard about it, they just got the wrong answer. Okay, and this is not smoking lesion. This is a complicated, time-dependent confounding version of smoking lesion. Okay? And my point is, I could keep going. I could make this much, much worse than this if I wanted, because the graphs can get arbitrarily big. Okay? And the point is, if you agree with 2, you can crank it out and get the right answer. And if you don't use causal decision theory, the onus is on you to get all these things right for all of these graphs. And some of these answers are not as obvious as smoking lesion at all. And I will give some examples of it in a moment. So here's another example, unresolvable confounding. The treatment here, so S is skyr. Skyr is a kind of Icelandic yogurt. It's really good, actually. It's, as a yogurt, it has intestinal flora in it. And for the purposes of this example, let's say that it's protective for stomach cancer. Okay? If you have Icelandic citizenship, you probably eat more skyr than the general population. So there's this effect, and Icelandic citizenship is not observed in this case. And it may happen that Icelanders, maybe have different rates of stomach cancer than the general population. So you have this confounding, and because we're not allowed to measure by the hypothetical, we have this problem that we can't really adjust for L because we don't see it. And so obviously the regular decision theory using conditioning will not work because there's confounding. Adjusting for B doesn't work because B is not a confounder, B is a mediator. It's between S and Y. So if we adjust for it, we're breaking the causal link from S to Y by just deseparation. We can try to measure L, of course, but that again is a non-starter because we're not allowed to measure things we don't see. That's silly. And it turned out there is the right answer exploiting B, the presence of this B that wasn't there in the smoking lesion case. And this is this formula, and it's relatively complicated. It's called the Frondor formula. I think Pearl figured it out first. And again, this is just a consequence of 2 for this graph. Okay? And again, this is not so easy to see. And it's not just like you have to condition on some things. You have to actually see what this functional is supposed to be to not get bias. Okay? And again, this example just has 4 nodes. I could make this much, much worse. So now let's get back to this claim that Bayesians like to make. Do we condition on everything? So here's my example. Q and R are not observed. The temporal order in which these things happen is Q, then L, then R, then L, then S, and Y. We only observe S, L, and Y. We want the effect of S, which is negative utility, and Y, which is positive utility. Okay? And the question is, so it seems like L is sort of like a confounder, and the question is, do we adjust for L or not? Now, Rubin, I will say that I don't fully understand Rubin's position, so this is my understanding of it. So maybe somebody will correct me if they know him. Rubin is a Bayesian. In the Bayesian setup, you condition on everything. In particular, you condition on L. So you look at the posterior given L under whatever his Bayesian setup is. Okay, that's what Rubin says. Pearl says, in this particular graph, if you accept 2, the potential outcome is just equal to Y given S. So in this case, correlation is causation, just because of the way this graph happens to be. And the way to think about it is there is this path from S to Y that looks like it's a confounding path. But because L has incoming arrows, if we don't condition on it, that becomes deseparated. And if it's deseparated, there is no bias. And so Pearl says, if you condition on L, you'll get bias. And if you ignore L, you will get the correct answer. And so this is his counterexample to the claim that you should always condition on everything. And his claim is that you only condition on things if it's warranted by the causal structure of the problem. So I'm not going to take sides here just to present these 2 sides and maybe ask for clarification from people who thought about it. I think Pearl has a point, but that's sort of the background I'm from. So there is a complete algorithm for CDT. I will not go into it in a lot of detail because that's a separate talk. But the point is that given a graph, an arbitrary graph, an arbitrarily large graph, and data that came from that graph, and this graph specifies a causal model, and given a set of outcomes Y and a set of treatments A, I could ask, what is the optimal thing to do for these actions to optimize the utility? So in other words, what's the answer here for that potential outcome Y given that I intervene on A, given that I decide on A? And there is a complete answer. And the only thing we need for this answer is to figure out what this guy is. And this guy happens to be this formula, which is not important to understand exactly what this formula does. this formula contains this weird operator that maps the data that we see into something else. I'll give some examples of it. The important thing to understand about this is that is two things. First, that it doesn't always work. Sometimes it will say that I can't give this to you in terms of the model that you gave me. You haven't given me enough information. Or it will give you a formula for this, a formula that's potentially very complicated. It's potentially much more complicated than just, oh, we have to condition on some stuff, and then things work out. Okay? So I will give you some slightly complicated examples in a second. And so if all of these operators succeed, then it will give the right answer, I claim. Unbiased answer, as the statisticians say. And if some of these fail, there's not enough information in the problem to solve it, at least given observational data. So here's a positive example. Here's a graph. It's still only 4 nodes with the utility node, so it's not that bad. And we're interested in, our action is on B and our outcome is D. And so the important thing here is on the bottom, because we need to compute what this quantity is to optimize utility with respect to it. And in this case, it happens to be this. So the thing to notice about this, so this is based on how this operator works. I'm not going to explain how this operator works, but there is a paper on it if you're interested. And why, but this is just consequences of 2. Consequences of equation 2 for this graph. The point about this equation is it's kind of weird looking, and there's more to this equation than just conditioning and things. There's multiplications, there are ratios, and this is all consequences of 2. And so the point is, getting an unbiased answer under this kind of causal model is not a simple thing. You can't just like sit in your armchair and think about it. You have to think really, really hard. And you notice in this case, you have so these red arrows represent unobserved confounders. And here we have some sort of confounder between the outcome and something that precedes the treatment. And we have this other weird confounder here. And the presence of these things in this particular form means that to get rid of all this confounding bias, you have to do very crazy things with your data, things that kind of look like that. And the point is, if you don't want to use CDT, you have to handle examples like this right somehow. And these examples are not so simple to get right without using causal calculus, which is what I'm using here. In other words, using 2. Consequences of 2. So that's one of my points. So if you want to generalize, so it's not so simple to say, oh, well, CDT fails in Newcomb. CDT gets a lot of things right too, and you have to just reuse, you shouldn't just reinvent the wheel. You have to see why it's doing that. Okay? Okay, and a negative example, I just wanted to point out that you can't always identify what we say, the guy we want from the data that we have. So in this particular case, we want Y given that we intervene in 8, but we can't actually get it from the data given this confounding structure. We need more information somehow. So there's not enough information to solve this decision problem. And what I mean by that is that I can give you 2 causal models that agree on the data and agree on the graph, but disagree on what the answer here should be. So it's hopeless, basically. Does that make sense? That's what identification means. If there are 2 things that agree on our inputs but disagree on our outputs, then there is no algorithm, basically. Yes?
So what do you mean by causal model?
I mean this. I mean equation 2. That's all I mean. So we can argue about whether we should adopt 2 or not. I have some reasons for adopting it that I give on the next slide. But you don't have to adopt it if you don't want. You can adopt some other definition if you want. But this definition has been very fruitful in statistics. Okay. And it agrees with intuitive answers in a lot of cases. And so I think that's a good reason for adopting it. And I have personally adopted it. But I understand that there is scope for argument here. Because, representative causality is serious business. And lots of people do it lots of ways. So the point of this talk is I'm giving you one way of formalizing what this funny double vertical bar distribution is. And I'm formalizing using this formula 2. That's called interventionist causality.
And given a causal graph, there's not necessarily just a single formula 2 is what you're saying?
No, formula 2, so given a single graph, there could be multiple. So I'm glossing over the fact that given a particular causal graph, there are lots of causal models, but all causal models all interventionist causal models will agree on 2 for this graph. So this is the minimum. Some of them assume other stuff on top of this that is not important for the purposes of this talk. But so if you want to argue with interventionists, this is what you argue about. You argue about whether 2 is sensible, and I think there is scope for arguing that it's not. So go ahead.
When you say that there are many models for the same graph, is what's different the p's on the right-hand side of 2, or are there other things that differ between those causal models?
What differs is assumptions that it makes on potential outcomes. Basically, it has a bunch of potential outcomes that it gets from 2, and then it says that some of them are independent of some other things. And the level of independence it's willing to assume varies between models. But we can talk about it after the talk. It's not central to what I'm trying to say here. Like Pearl assumes a lot more independences than some other people would, because Pearl is a computer scientist and he feels that circuits you could figure out. Basically, you could figure out cross-world things in a circuit. Anyways, it's not important. It's all about your. Okay, so where am I? Am I here? Yes. Yes, this is where I am. So yeah, my point was that. So all of this crazy stuff I'm doing, it all assumes 2. So I'm asking of you your indulgence in saying that 2 is a reasonable way to do causality. Okay, so causal graphs in CDT. Humans have strong visual processing and weak symbolic processing, and what I hope I illustrated with a few of these examples is it's very easy for me using these graphs rather than stories, as is typically done in analytic philosophy, to construct very complicated examples that are with very subtle answers. Okay, an interventional CDT using 2, assuming you think 2 is sensible, gets a lot of them right, and it's used in practice. So people who worry about in Britain, people worry about how whether a particular treatment is worth it. In other words, maybe it's good, but it's also expensive. So that's like a typical decision problem in medicine. Like, do we give this treatment? And so when they think about these problems, that's what they use. So this is out there in the trenches. Okay, so the question is, why start from scratch? And the proposal is, if you wanna think about orthopics and you wanna think about Newcomb, you generalize this, because this already works on lots of stuff. Okay, and what I hope that I showed you is it works on lots of stuff that's a lot more complicated than just a smoking lesion problem, which is the simplest thing you can have, the 3 nodes. In fact, you can have 30 nodes. Yeah? But what about Newcomb's problem? Okay, so this is sort of the last part of my talk. So Newcomb's problem is about a magician named Omega who thinks that he can predict what you're going to do. And so the question is, do we 1-box or do we 2-box? And I will assume for the purposes of this talk that 1-boxing is what's sensible to do. Okay? And so EDT 1-boxes because of that, and ICDT 2-boxes because it does not take, so I will get back to this point in a second, but basically, from a point of view of an interventionist, an intervention is an absolute act of free will imposed from the outside, not amenable to analysis by an outside party. And so another way of saying it is they don't take Omega seriously, and so they 2-box. And people have been criticized CDT, and I think the criticism applies to the version that I've presented with interventions, which is that it doesn't do the right thing here. Okay, and so how could we respond to this criticism? Well, we could beg off on definitions where I've heard some people do that, where rational means you agree with CDT, which is silly. So I agree that this is silly. That's all I'm going to say about it. Another argument is from perversity, which is that this problem sort of maliciously punishes otherwise rational behavior. And I'm slightly more sympathetic to this because it is quite rational to use CDT in lots of sort of medical settings that are not exotic. But I'm not sympathetic because it seems like it's fighting the hypothetical, basically. So, okay, well, what if there is a magician? We should be sensible anyways. And and people argue also sometimes that there are sort of everyday versions of Newcomb as well. And so the other option is to give up, is to say that there are local optima but no global optima in a decision theory landscape. In other words, sometimes one is sensible and sometimes another. And maybe that's true, but I think that's too pessimistic for now. It may turn out to be true with more work. And so the other thing to do is to try to repair CDT somehow. That's what I will talk about. Okay. So let's go a little meta, as they say, and think about why is it that decision theories fail. So EDT fails in smoking lesion. This is well known, at least the version of EDT that I'm talking about here, with conditional probability. It's very naive. So the reason this naive EDT fails is that it cannot represent the problem. In particular, it does not know what confounding is. And smoking lesion is all about confounding. So it fails. That's not surprising. It tries to use conditional probabilities for something that you shouldn't use conditional probabilities for. Okay, ICDT, so my version of CDT that I've presented, fails into Bunbox and Newcomb because it cannot represent the problem. In other words, it cannot deal with the fact that omega is actually not lying and it can simulate you or use some other exotic means of actually figuring out what you will do in advance. And so one point I want to make is EDT, so CDT is actually strictly more powerful than EDT in terms of representation power. The reason for that is because one of the assumptions of equation 2 is also equation 1. Equation 1 is the statistical version, and that's what EDT assumes. And so actually 2 subsumes 1. And so what that means is that EDT cannot represent Newcomb-type problems either, in general. It's just that it happens to be right on this particular version of a very general class of problems with omega. And so my claim is it's sort of right by accident. And so I will give later an example of Newcomb that both has omega and has confounding, on which EDT will fail, at least in naive EDT. Okay, so we can argue about it. But my claim is that the issue is representational. So what you should be doing is not going back to EDT, because EDT just fails on an infinite list of examples that I gave. But to try to figure out what it is that we're not representing about Newcomb and just represent it. That seems to be the right approach to me. Okay, and so I think what we need to do is we need to talk about decision algorithms more. That's really what this is about. But we also need to think about causes and effects still. So we're going to reify decision algorithms. That's a very fancy way of saying that I'm going to draw a box on my graph, and that's going to be my decision algorithm. It's not a very fancy thing. This is called an influence diagram. This is like back from the 70s. This is very old technology. So this is just an indicator for what we're going to do. So if S is little s, that means that we chose to do S. We exercise our free will. That's like an intervention. And if S is S prime is the empty set, that means that we kind of left the system alone and let L determine what happened to S. Okay, that's sort of the domain of naive evidential decision theory. This is something Phil David likes to do as well, by the way. So we can optimize over S prime, and that just recovers interventional decision theory just with an extra node, basically. In particular, in this particular case, which is, if you remember, is a smoking lesion problem, we just get our adjustment for L. I just gave that derivation involving that indicator, but it's basically the same answer as before. And the crucial assumption is that our indicator is independent of the outcome given our action. And it's independent of L. In particular, if you look at this graph, our decision algorithm only influences the world through our decision, which in non-exotic cases is a very sensible thing to do. That's what usually happens. But the point is, that's not what happens in Newcomb. In Newcomb, our decision algorithm influences the world twice, through our decision and through omega. So the point is, there are two ways to do a diagram of Newcomb. We can take omega seriously, or we can not take omega seriously. If we don't take omega seriously, then there is no link from D prime to omega, because we think, I'm sorry, omega, I don't believe your claim. I have free will, and I can choose to do what I want, and I don't think you can predict what I'm going to do. So that's the bottom view. And depending on who omega actually is, maybe omega is a charlatan, so maybe that's actually right. But if omega is actually a magician, like he claims, then actually that's an erroneous view. And actually what's right is the view on the top, where it's true that your decisions affects what you will actually do, but it will also affect omega, because omega can simulate you in a fine enough level of detail that he is not wrong. And so, CDT assumption that your decision algorithm just influences you through your decision, which is explicitly given by Phil David in his papers, just fails on this problem. So your representational assumptions are just not right. So to me, the right answer is to relax this assumption and keep all the other goodies than to go back to EDT. Okay? So, extending CDT for Newcomb problems seems to me to be very easy. We just draw the influence diagram and we add exotic causal relations in. Like, you know, omega can read my mind in advance. So you just add the extra arrows in, and then you optimize over the indicators for the best utility. And in this case, that will trivially one box, because then it just becomes, I mean, I've done nothing here. I've just said, look, let's take seriously what he's saying. But the point is, it's still a causal graph. I'm not using EDT here. I'm just using CDT and taking omega seriously. Okay? So we directly represent both standard relations and exotic causal relations, and then just do our optimization. So, so that's that. So now let's keep going and see why I think it's not good enough to just use EDT for these problems. Because the point is, I have a graph and I can make factories of things. In particular, I can make factories where omega can read my mind, complicated ones. And I can surely come up with something that will trip EDT up because it's not doing confounding properly. So let me do a simple example that comes up in statistics. And this example is non-compliance. So there's a slight digression, but you'll see that it's related. Non-compliance is this important problem where we tell people to do something and then they don't do it. In other words, we tell people that you should take this drug because you're in the chest arm of the trial, but they say, I forgot. So this is a real issue, and people worry about this problem very seriously in statistics. Because non-compliance, like if you Google for non-compliance, you're gonna get a ton of papers on this. And this is the graph that it looks like, except that people don't draw the U, but that's not important. So L is the kind of person you are. And people think of it, so D is my decision. This is like the experimenter telling the person take the drug, and D is whether they did it or not. And then B is what happened to them. And you could have four kinds of people. You can have compliers. These people do what you tell them. If you tell them to take it, they'll do it. If you tell them not to take it, they won't do it. Some people are defiers. They don't like authority. They do the opposite of what you tell them. Some people are never takers, and some people are always takers. It turns out that without loss of generality, you can think of your people as divided into these four groups. Sometimes people assume that defiers don't exist. That's like an assumption. And so the point is, your drug may affect the outcome differently depending on what group you're in. That's just standard confounding problems, right? And so the intention to treat effect is what they call this in the literature is what's the effect if we decide, what the effect of us telling people to take the drug. That we can easily do because this is not confounded with anything. That's randomized. Because we randomize telling people whether they should take the drug or not. But what we actually want is the effect of actually people taking the drug. And that is confounded by something that we don't see. Okay, so these are not the same effect at all because of this confounding issue. And so this is not actually identifiable from this data in general because that operator I told you about will fail on it in this graph. But this is identifiable with some additional assumptions called instrumental variable assumptions. That's also a very important part of causality. And we can also get bounds on it, which sometimes is good. So this is the end of the slide digression. Now let's go back to Newcomb, given non-compliance. So that's how I will introduce confounding into the Newcomb problem. So this is a bicameral decision problem. So in this bicameral, thank you for coming. So in this bicameral decision problem, we have two agents, the master and the servant. So I have left deliberately unspecified who these guys are. Maybe they're a part of your soul. Maybe they're two different people in a trial, the experimenter and the person. And there are four types of servants: compliers, defiers, never takers, and always takers. And there's an even split of them in the population. And so compliers and defiers activate when the master decides to do something. And compliers do what he says, and defiers don't do what he says. And if the master is silent, they just flip a coin, because they don't care. Okay? Compliers and always takers live, and the others die, based on the drug. So in other words, there is no error from D to B. In fact, it's just L that determines whether you live or die, the kind of person you are. Okay? So the question is, do we take the pill or not in this problem? Okay? So I'll introduce omega in a second. So here's an EVDT solution. Given that they flip a coin and there's an even split in the population, this is my joint distribution. I can compute from this joint distribution conditional distributions, and that's what naive EVDT does. And naive EVDT says, oh, look, I'm more likely to live if I take. I take. Bam. Okay, this is obviously not right because of the standard confounding issues. So naivety solution is we just look at what happens if the master decides. That's the intervention. So master can decide to take, or the master can decide to refuse. But because we have this non-compliance, we won't get complete correspondence between what the master decides and what actually happens. And we just see that regardless of what the master decides, there is no effect on survival, and that's because it doesn't matter if you take the thing, it just matters the kind of person you are. And so it seems sensible that naive EDT answer seems more sensible to me, right? Because
Sorry, naive EDT?
naive CDT
Okay.
Answer seems more sensible because the drug does not affect survival, so it doesn't matter. And so that seems to kind of capture that, okay? Okay. So now let's do Newcomb's problem with non-compliance. We'll introduce Omega, who will maliciously read the master's mind and modify the outcome. So you'll say, I'll just OR your survival with whether the master decides to do something. So this is not very, it doesn't have the intuitive force of Newcomb's problem, but the point is, because it's not so hard to think of a compelling case, but the point that I'm trying to make is that I can just construct a graph where Omega reads your mind and modifies things. And the point is that to correctly represent this version of a Newcomb-like problem, you need to do two things. You need to first take Omega seriously, and second, you need to understand enough, you need to have a rich enough language to understand what confounding is, to understand that L is a confounder. You need to do both of those things correctly to get it right. Okay? So what should we do in this case? So naive EDT ignores the master because my naive EDT just looks at what happens naturally, and you just get the same probabilities as before. Naive CDT does not take Omega seriously, so it thinks there is no preference because of this, because thinks Omega is lying. And both of those are not sensible in this case. And so the right answer is we just look at the at what happens in the graph where we add the arrow from the decision outcome to Omega, and then we see that we just will always live if we refuse, whereas we only live half the time if we take. And so it seems sensible, given the setup, that we should refuse the setup. It seems sensible to refuse. So the point of this example is that to solve this example, I modified CDT, so I still am handling confounding, but I'm also handling the causal relationships, exotic causal relationships given by the setup of the problem and given Omega's omnipotence. And so the claim is that this is just a simple example with, 6 nodes. I could make this 30 nodes, and it's going to get much, much worse. And to handle it properly, you still need to handle causality properly, to do all the confounding in this complicated graph properly, which, as I've convinced you earlier, sometimes involves very complicated formulas indeed of the observed density. Okay. So, now this is the last slide, more or less. The claim is that decision theories failed because they don't represent the problem really. So we need to represent the problem properly. The version of EDT I presented is, of course, a straw man for rhetorical effect. There are obviously more sophisticated versions, but if you really want to steel man EDT, you gotta do a lot of work because of all these examples I show you that have sophisticated answers that are not. So I actually had this conversation with Paul, where we ran out of time, where I gave him the healthy worker survivor effect example and said, okay, you're a Bayesian, Paul, figure the right answer for me, or tell me why my answer is wrong. And it's not so simple, even in that case. Without talking about causal concepts, which you're not allowed to do if you use EDT. Because if you're doing causal stuff, you're doing CDT, to me. Okay, so I think that a sensible EDT that solves all the stuff that all these obstacles I've put in its way will just end up being isomorphic to CDT, or at least the version of CDT that I presented. And so am I wrong? So one of my questions to you guys is there a serious CDT alternative, maybe some sort of Bayesian one, that actually is qualitatively different and still does sensible things in all these crazy examples of crazy confounding? I'm not sure. I'd like to know the answer to this question. So interventional CDT is quite well developed. There's a complete theory. I'm sort of partially responsible for it, which is why I'm talking about it. It's very successful. It's used in practice for deciding if the drug is worth giving, for things like that. So the claim is interventions are the right thing. That's talking about equation 2. So we could argue about whether this is sensible or not. I think it's sensible, and a lot of people agree in stats. Causal graphs are good because they are a visual thing, and they are a general mechanism for just constructing examples. very complicated examples with very tricky answers. And I think, and they help you because your vision system is strong, they help you from getting lost. So my suggestion based on all this is, if we want to do exotic things, we need to extend the thing that works to handle it by just adding the representational features that we need. Maybe indexical uncertainty, who even knows? Maybe omega, maybe other things that people who work on UDT think about. And so that's it. Thank you very much.